Am I right? So in last lecture, what we have discussed? We have discussed AAC1. That means acid catalyzed My screen is visible to everyone? Okay. So in last lecture, we have discussed AAC1, that is acid catalyzed acyl oxygen bond breaking unimolecular. Okay. And I told you that AAC1 proceeds only those molecules which are able to form a stable carbocation. Okay. So we can easily explain the esterification, even the ester hydrolysis of sterically hindered molecule. In order to explain AAC1 ester hydrolysis, we have taken the example of methyl mesitoate. Methyl mesitoate is able to form a stable carbocation, that is acylium ion. Okay, and the esterification that we have explained through taking the example of mesitoic acid. And first mechanism that we have discussed is ester hydrolysis, that is AAC1. When methyl mesitoate is first treated with acid and water, get hydrolyzed and gives mesitoic acid and methanol. What will be the mechanism of this reaction? So first, methyl mesitoate first get protonated and gives protonated ester. So this oxygen contains two lone pairs. One of the lone pair get protonated and gives the protonated ester. This is the first step, and the first step is protonation. The protonation step is always fast. The second step, what happened? Now this protonated ester contains a good leaving group, that is methanol. So it leaves from the molecule and forms acylium ion. And forms the acylium ion. Now this acylium ion is an intermediate and is a stable intermediate. And the second step is a rate determining step. And the rate determining step involves only one species, that is a protonated ester. And that's why this hydrolysis is referred as a unimolecular reaction. What happened in the third step? The water molecule attacks on this positively charged carbon, gives protonated acid. And the last step is a deprotonation and gives mesitoic acid. So the forward reaction is ester hydrolysis, while backward reaction is esterification. So in ester hydrolysis, the second step is a rate determining step, means the rate of the reaction depends on concentration of ester only, and the rate determining step involves only one species, that is ester. And that's why the molecularity of this reaction is a 1, means unimolecular reaction. And the order of the reaction is a first order. The second mechanism that we have discussed is esterification through the AAC1. So first the mesitoic acid get protonated, gives the protonated acid. Now this protonated acid again contain a good leaving group, that is water molecule. Water molecule is a good leaving group. So it leaves from the molecule and gives stable intermediate acylium ion. This acylium ion then attacked by nucleophile methanol. Because methanol contains oxygen, and this oxygen has two lone pairs. And the lone pairs are also a source of electrons. And gives this protonated ester. And the last step is a deprotonation. Gives the methyl mesitoid. So this is a mechanism of esterification, in which the second step is a redetermining step. In redetermining step, if you observe clearly, only one species is involved, that is the protonated acid. So the esterification is also unimolecular reaction and also first order reaction. So let's move further. So we have discussed the rate of ester hydrolysis, even rate of esterification. So rate of ester hydrolysis and the rate of esterification. Rate of ester hydrolysis. It depends on only the concentration of one species, that is ester. Even the rate of esterification depends on concentration of acid. So we are talking about AAC1. So rate determining step involves only one species, whether it is ester hydrolysis or esterification. That's why both this mechanism follows unimolecular. Both are unimolecular reaction. Simply means that esterification or esterohydrolysis of sterically hindered acids like 2,4,6-trimethyl benzoic acid can be explained by AAC1. So whether it is ester hydrolysis or esterification, whether it is ester hydrolysis or esterification of sterically hindered acid, like 2,4,6 trimethyl benzoic acid, 2,4,6 trimethyl benzoic acid can be explained by mechanism that we have discussed earlier, AAC1. But esterification and the ester hydrolysis of benzoic acid cannot explain by AAC1, because benzoic acid is not able to form a stable carbocation, while 2,4,6 trimethyl benzoic acid, mesitoic acid, This is also known as a macetoic acid. Is able to form a stable carbocation. Okay. Now, why this carbocation formed by 2,4,6-trimethyl benzoic acid is stable? So this carbocation is formed when we carry out the hydrolysis, even the esterification of macetoic acid. And here we have methyl groups 2, 6, and 4. So this is the intermediate is formed. And this is known as acylamine. Okay, now this acylamine is stable by the lone pair of this oxygen, because this oxygen contains 2 lone pairs. Okay, and this carbocation contain vacant p orbital. So when this lone pair is donate to the vacant p orbital of this carbocation, what we get? We get one resonating structure like this. Now, oxygen contains positive charge. Here we have methyl. Here we have methyl. Here we have methyl. So this acylamine stabilized by the lone pair of this oxygen. And this effect is known as a mesomeric effect. Yes? Just wait. दे रहे होगी, दिखाए, दिख रही है ना? आप देखो ठीक से. Okay. So this effect is known as a mesomeric effect. And if you look at this cation, octet of this carbon is not completed. Only 6 electrons in their outer shell. 1, 2, 3, 4, 5, 6. Only 6 electrons in their outer shell. Six electrons in the outer. But in this structure, the octet of carbon as well as the oxygen is completed. Look at this here. 1, 2, 3, 4, 5, 6, 7, 8. And oxygen also has one lone pair. Now count the octet electrons in the outer shell. 1, 2, 3, 4, 5, 6, 7, 8. Means octet of carbon as well as oxygen are completed. That means now this cation is more stable. More stable. So this cation is stabilized by mesomeric effect and also stabilized by hyperconjugation, because we have 3-methyl group at ortho and para position to this cation. So I can also write this methyl group in this fashion. Here we are also having the methyl group. Here we also have methyl group. Now this methyl group can take part in the hyperconjugation in this fashion. When this electron carbon hydrogen bond transfer here, this bond transfer here, we also get hyperconjugated structure. So here we have double bond, here we have double bond, now here we have double bond. So H, H, and now here we also having the double bond. We get this structure. So this is known as a hyperconjugated structure. And this hyperconjugated structure is not possible in case of benzoic acid. If I draw the structure of benzoic acid, this is the structure of benzoic acid. Similar to the macetoic acid, this is the structure of macetoic acid. So the part of comparison between the benzoic acid and macetoic acid is a methyl groups. Okay. Now this benzoic acid, when undergo the esterification, it leads to the formation of acylium ion. So this acylium ion is only stabilized by the mesomeric effect, like this, as I said earlier. But here, this benzoic acid not contains methyl groups. So hyperconjugated structures are not possible in case of benzoic acid. Okay, but not only this carbon-hydrogen bond take the part in the hyperconjugation, this carbon-hydrogen bond also take the part in hyperconjugation, and this carbon-hydrogen bond also take the part in the hyperconjugation. Similarly, these three hydrogen atoms also take the part in the hyperconjugation. Similarly, these three hydrogens also take the part in the hyperconjugation. So please tell me, how many hyperconjugated structures are possible? How many hyperconjugated structure is possible? How many hyperconjugated structure are possible? So the proton is eliminated from here is nearby. That's why hyperconjugation is also known as a no bond resonance. So how many hyperconjugated structure are possible? So in the first hyperconjugated structure, this carbon-hydrogen bond take the part, then this one, then this one. So three hyperconjugated structures are possible from this methyl, 3 from this and 3 from this. That means total how many? Total how many hyperconjugated structures are possible? Total how many hyperconjugated structures are possible? Do you understand my concept? Yes or no? Total how many hyperconjugated structures are possible? That's a simple question. One answer is 10. Please answer on chat box. How many hyperconjugated structures are possible? This is the only difference between the benzoic acid and macetoic acid. Because stabilization to the mesomeric effect is also possible in benzoic acid. But benzoic acid cannot give the hyperconjugated structures. So please tell me how many hyperconjugated structures are possible. Yes, yes. कितने पॉसिबल हो सकते हैं? Yes, go ahead. How many alpha hydrogens are possible? So this total 9. Okay, very good. So total 9 hyperconjugated structure are possible. Okay, and this okay, go ahead, please. Yes, yes. No. हाँ, हाइपर कॉन्जुगेटेड स्ट्रक्चर किसने पॉसिबल? ओनली 9 पॉसिबल है, 10 नहीं होता. दिस इज ना, किसमें पढ़ा था आपने ऐसा? ऐसे कितने, जस्ट ओके, आई एम टॉकिंग अबाउट हाइपर कॉन्जुगेटेड स्ट्रक्चर. ऐसे कितने स्ट्रक्चर पॉसिबल है जो यहाँ पे मैंने ड्रॉ किए है? ऐसे कितने पॉसिबल है? इसकी मैं बात नहीं कर रहा हूं, मैं हाइपर कॉन्जुगेटेड स्ट्रक्चर्स की बात कर रहा हूं. दिस इज नॉट अ हाइपर कॉन्जुगेटेड स्ट्रक्चर, दिस इज हाइपर कॉन्जुगेटेड स्ट्रक्चर. हाउ मेनी पॉसिबल? 9 है ना. सो हाइपर कॉन्जुगेटेड स्ट्रक्चर इज ओनली 9. ओके, गलत है, गलत है, गलत है. हाइपर कॉन्जुगेटेड स्ट्रक्चर जब आपको पूछा जाता है, योर आंसर विल बी 9, नॉट 10. 10 हाइपर कॉन्जुगेटेड स्ट्रक्चर बन ही नहीं सकते ना. तो ये हाइपर कॉन्जुगेटेड स्ट्रक्चर मींस क्या होता है? दिस कार्बन हाइड्रोजन बॉन्ड मींस ओनली sp3 hybridized carbon take the part in the hyper conjugation. Means these 3 hydrogens, these 3 hydrogens and these 3 hydrogens. So only 9 hyper conjugated structures are possible. Only 9, not 10. Hyper conjugated structure means how many structures are possible? This kind of how many structures are possible? Only 9. Only 9. First, you have taken this hydrogen, carbon hydrogen, then take this carbon hydrogen, then this carbon hydrogen. So 3 from here, 3 from here, and 3 from here. So only 9 hyperconjugated structures are possible. Okay. So that's why this acylium ion is more stable. This acylium ion is more stable than this acylium ion. Am I right? So acylium ion formed by mesitoic acid is more stable than formed by benzoic acid. Am I right? This will be more stable. That's why we can explain the ester hydrolysis, even esterification, through the AAC1 only in case of mesitoic acid, not for the benzoic acid. Concept समझ में आ रहा है? Understand my concept? Yes or no? Understand the concept? Why benzoic acid cannot give ester hydrolysis or esterification through the AAC1? The reason is the formed acylium ion is less stable than that of acylium ion formed by mesitoic acid. Concept is clear? Yes or no? Why acylium ion formed by mesitoic acid is more stable than that of benzoic acid? Why this acylium ion is more stable? Because here the mesomeric effect is there. So this is not a part of comparison. This is not a part of comparison. Part of comparison is 9 hyperconjugated structures. Shall we move further? Shall we move further? Okay. Now next mechanism that we are going to discuss is AL1. What means of AL1? That is, A stand for acid catalyzed. What means of AL? What means of AL? Oxygen alkyl bond, okay, or alkyl alkyl oxygen bond fission. What means of one? One stand for unimolecular. One stand for unimolecular. Okay. So whenever the unimolecular reaction is there, is always proceed through the stable intermediate. Always proceed to the stable intermediate in organic chemistry. Okay, most of the reactions. Okay, so the AAL1 that we are going to explain through the tertiary butyl benzoate by taking the example of tertiary butyl benzoate. So ester like tertiary butyl benzoate. So this is known as a tertiary butyl benzoate. When this tertiary butyl benzoate undergoes the hydrolysis, because the acidic condition, hydrolysis is a reversible reaction. H plus water molecule hydrolysis. What it gives? Acid plus alcohol. What do we get here? Benzoic acid and tertiary butanol and tertiary butanol. Okay, so hydrolysis, even the esterification of this type of esters followed AAL1 mechanism. Because when the alkyl oxygen bond, that means this bond, when this bond is formed, this will convert into the cation. And we know that when it forms this cation, it is a tertiary cation. And we know that the tertiary cation is stable because of the inductive effect and hyperconjugation. So this is the concept of AL1. So here we are going to use tertiary butyl benzoate. So this ester is formed by benzoic acid and bulky alcohol, that is tertiary butanol. And the product, another is benzoic acid. Okay, this is the hydrolysis. This is a now how we can prove that in AL1 or tertiary butyl benzoate hydrolyzed through the AL1 mechanism. Okay. For that, this tertiary butyl benzoate, when hydrolyzed with the water, but the water oxygen is labeled, means we have taken the isotopes of the oxygen, O18. When we hydrolyze this tertiary butyl benzoate in presence of acid or acid as a catalyst, what we get? Benzoic acid and tertiary butanol. But this labeled oxygen with the alcohol. This labeled oxygen with the alcohol, not with the acid. Okay, so what happened here? If I write this water molecule in this fashion, I write this labeled oxygen in different color, so you might aware. Okay. Now during this hydrolysis, alkyl oxygen bond is break. So this part will convert into the acid, and this part will convert into the alcohol. In order to convert this part into the acid, we need the hydrogen. So this part will take the hydrogen here, and this part will take the OH from the water molecule. In that way you can remember. So now this labeled oxygen with the alcohol and the labeled with oxygen with the alcohol prove that during the hydrolysis, alkyl oxygen bond was break. Is it clear? Is there any doubt how we can prove that during the reaction alkyl oxygen bond is break? By reaction with water, but the oxygen of the water is labeled with isotopes of the oxygen, that is 418. Now this labeled oxygen in the product with the alcohol, that is tertiary butanol. Tertiary butanol. And this can be easily determined by mass spectrometry. Mass spectroscopy. Because isotopes we can easily determine by the mass spectroscopy. Okay, is it clear? So we can only explain the hydrolysis of tertiary butyl benzoate through the AAC1 mechanism. So when the alkyl oxygen bond is break, it leads to the formation of stable carbocation, that is tertiary carbocation. Okay, let's see the mechanism. What is the mechanism of this reaction? Mechanism of the reaction. So this is a tertiary butyl benzoate. We are talking about acid catalyzed hydrolysis. So reaction first carried out in presence of acid. Now, the lone pair present on this oxygen as well as this oxygen. Now, lone pair present on this oxygen is sterically hindered because of this 3 bulky methyl group. So this lone pair is present on the adjacent carbon, and this carbon attached with the 3 bulky methyl groups. So this lone pair is sterically hindered. So this lone pair cannot easily get protonated because of the bulky methyl groups. You might wondering why this lone pair not get protonated. Why this lone pair? The reason is this lone pair is sterically hindered because of these three bulky methyl groups. So one of the lone pair get protonated here. One of the lone pair get protonated here. Again we get protonated acid. Here we have three bulky methyl groups. And this is a protonation step. And the reverse step is a deprotonation because acid catalyzed hydrolysis is always reversible. So the reverse step or backward step is a deprotonation. Means elimination of H plus. Elimination of H plus. Now what happened in the next step? This is very important. This bond, this alkyl oxygen bond is now going to break. This bond will transfer here. And this electron now transfer here. And positive charge of the oxygen get neutralized. So what happened here? So double bond now becomes single bond, so OH here, and here we get double bond O, and what we get? Carbocation. Because you can write this carbocation in this fashion. So after the bond is break between oxygen and carbon, what we get? Acid and carbocation. And this is a tertiary carbocation. And tertiary carbocation, we know that it is a stable carbocation. Now the reverse step, what happened? This lone pair can attacks on this carbon, positively charged carbon. What do we get this step? So the formation of this carbocation is a rate determining step. So this is a rate determining step. Again, the second step is a rate determining step, and it is a slow step. What happened in the backward reaction? This lone pair attacks on this carbon. Okay. Or you can also like form like this when this lone pair comes back. This lone pair now attacks here. What do we get? This step. Or you can say this bond. Okay. Let's write, this is wrong. So when this electron transfer here, this will attack here. You get this step. And this step is a fast step. is a fast step. So the second step is a rate determining step and it is a slow step. But the backward reaction is a fast reaction. Okay, now what happened in the last step? This carbocation is then attacked by water molecule. Oxygen has two lone pairs. One of the lone pair now attacks on this carbocation. And finally, deprotonation, what we get? OH, methyl. Methyl. And okay, so this carbocation is planar. So water molecule can attack from the front side as well as from the back side. But here you get the same product because this carbon is not chiral. If this carbon is chiral, you get the racemic mixture because this carbocation is planar. So this water molecule may attack from front side or from back side. You get the racemic mixture in case of chiral carbon, but this carbon is not chiral, you get the same product, whether it is attacked from front side or from back side. And we have already added the acid in the reaction. So when acid gets protonate this OH and the OH is eliminated, what you get? Carbocation. So elimination of water molecule forms the carbocation. Because this reaction carried out in presence of acid. So acid protonate this OH, which is then eliminated and forms a stable carbocation. So this step is also reversible step. Okay, so let me write separately this carbocation. Now, if this carbocation is attacked by water molecule and the reaction condition is acidic, because we are talking about acid hydrolysis, and if we have added labeled oxygen or water contain the labeled oxygen or isotopes of the oxygen. Now this oxygen also contain two lone pairs and one of the lone pair attacks on this carbocation. Now, as I said earlier, this carbocation is planar. So this water molecule can attack from front side or attack from back side. So this is a front side attack. Front side attack. And this is a back side attack. Back side attack. Front side attack and back side attack. Yeah. But here you get the same product. Here you get the same product because this carbon is not chiral. And here we get labeled oxygen. This is the one product. when it attack from the front side, when attack from the back side, you also get the second product. So this product will form by front side attack. This will form by back side attack. But in this case, both products are same because this carbon is achiral. If it would chiral, then we get the racemic mixture. Then these two products are different. This chiral with this carbon is chiral, and the form product are different. We get the racemic mixture. Okay, so now if you look at this labeled oxygen is with the alcohol, not with acid. So during the reaction, what happened? Alkyl oxygen bond is break. Alkyl oxygen bond is. Is it clear about Al1? So during this reaction, alkyl oxygen bond fission is takes place. And how we have proved that during the reaction, alkyl oxygen bond is break with reaction with water with labeled oxygen. Then this labeled oxygen with the alcohol, not with the acid. So this reaction proves that during the hydrolysis, alkyl oxygen bond is break, not a acyl oxygen. Okay. Is there any doubt in this mechanism, Al1? It is only occurs in those molecules which are able to form a stable carbocation. And this mechanism we have explained through the Al1 of tertiary butyl benzoate. Is it clear? Is there any doubt in this mechanism? Is there any doubt in this mechanism in Al1? So let's talk about the rate determining step. Let's talk about the rate determining step. Which is a rate determining step? Which is a rate determining step? Second step is a rate determining step. So the rate of the reaction is depends on concentration of only ester. Concentration of ester. Because in rate determining step only ester is involved. So that's why only one species is involved in rate determining step. That's why this reaction is unimolecular reaction. And this is also first order reaction. So first order reaction. So AAL1 follows first order kinetic. Okay. So what happened in the first step of this mechanism? Ester get protonated. The second step, the slow and a rate determining step in which alkyl oxygen bond fusion is take place. Then the resulting in the formation of acid and the stable tertiary cation. The reaction then proceeds the fast addition of water molecule to the carbocation and gives tertiary butyl alcohol. Okay, and of course this reaction is a reversible because we are talking about acid catalyzed reaction. So this tertiary butyl alcohol and this benzoic acid in acidic condition form tertiary butyl benzoate. That means the reverse reaction of this ester hydrolysis shows the mechanism of esterification. Is that clear? So reverse reaction is a esterification. Again in esterification, the second step will be the slow step and it will rate determining step. And in rate determining step, only one species is involved. That's why the esterification is also a unimolecular reaction. Okay, what happened in first step? So alcohol first get protonated, gives the tertiary butyl carbocation. What happened? This tertiary butyl alcohol get protonated, water molecule is eliminated, gives this tertiary butyl cation. Then this acid attacks on this carbocation, form this protonated ester. Then the deprotonation gives ester. So the reverse reaction is esterification. Okay, what happened in the first step of esterification? This tertiary butyl alcohol get protonated, gives the cation. Okay, let me write here. In esterification, what happened? First, this tertiary butyl alcohol in presence of H plus gives protonated alcohol. Second step, what happened? Water molecule is eliminated. By elimination of water molecule, give tertiary butyl cation. Is that clear? Now this step, second step, is RDS. This step is RDS. So in RDS, only one species is involved, that is alcohol. That is alcohol. Now what happened in the next step? Benzoic acid, now like this fashion, this lone pair falls here, this will attack on this carbocation. This is also reversible step. And gives, so here we have double bond, OH remain as it is. The lone pair is transferred here, that's why positive charge. Now this oxygen forms a bond with this cation. The last step is deprotonation. Last step is deprotonation. And this is the mechanism of esterification. This is not in your syllabus. This is the mechanism of esterification. So in esterification, rate is only depends on concentration of alcohol. That's why it is also unimolecular reaction. Unimolecular reaction. Okay. So this is all about AAL1. So we will continue this AAL1 in next lecture. If you have any doubt, you can ask me. This mechanism not in your syllabus, just for your information, just for your knowledge. So this mechanism in your syllabus, the ester hydrolysis through the AAL1, not a esterification. Esterification is not in your syllabus. In your syllabus, only the ester hydrolysis. Is there any doubt in this mechanism that any step you cannot understand? Till then, thank you very much, all of you. Have a pleasant learning of organic chemistry. Thank you. Thank you very much, all of you.